thank you all for coming. I'm very excited to be here, obviously. Today we're going to talk about Prometheus and scaling Prometheus with Thanos. It's obviously a big subject, so we will try to focus on some of the hidden costs that we bumped into when we did the migration. Some introduction. My name is Daniel Gur. I've been working for Outbrain as the observability team lead for the last 5 years or so, and I'm doing DevOps. DevOps since I'm 16. Do the math. That's it. Let's start. So some numbers about Outbrain. I will just explain the scale that we work with, because eventually it will explain some of the decisions we took in our architecture. So we scraped around 300 million metrics per minute, and we also have around 60 engineering teams across the R&D organization. So to tell our story, I need to give a bit of a background about how Outbrain works and what we did in the past. So Outbrain has around 8,000 physical servers, and we work in a hybrid environment, which means that we work with physical servers and with GCP and Azure. So because our core infrastructure is physical, obviously also our Prometheus infrastructure was physical. So the basic architecture that we had was that each of the 60 different engineering teams had its own physical server, and obviously we also wanted DR, so it means 120 servers to feed the Prometheus infrastructure. The retention that each server had was between 14 and 30 days, and it obviously depends on the amount of metrics that each team had produced, and the memory and the disk space that we had on the physical servers. Except that we didn't have any long-term solution, which means that if a developer wanted to, look on its trend of the metrics that he has like 3 months ago, he just could not. Okay, what's wrong? I believe that most of you would say everything, and I believe that most of you would say that because of the physical infrastructure. And nevertheless, your opinion with physical infrastructure, eventually, the main issue with that, in my opinion, is the lack of scalability. Because, it's hard to scale. Sometimes you cannot because you maxed out the number of DIMMs that the physical server can have. It's a mess. So Thanos happened. Thanos is, and I'm quoting, a highly available Prometheus setup with a long-term storage capabilities. At a glance, Thanos is a CNCF project that allows you to upload time series data into S3 compatible storage, and because that storage is cheap, you can save it to longer terms. Thanos knows to query data both from Prometheus and the S3 bucket simultaneously. We will talk about it. And Thanos is also Prometheus compatible, which means that you can take Thanos, put it on top of every Prometheus existing infrastructure, physical, virtual, it doesn't matter, and it will just work. In practice, Thanos does a lot more than that. Thanos, actually, the project took some of the responsibilities of Prometheus and broke them apart, and each responsibility now resides within a different service, and therefore it can be easily scalable. One example is Prometheus has 2 responsibilities. One, it has a lot more, but one is for creating recording rules. Recording rules is just the way that you take some PromQL, which has a very heavy computational effort. And because of that, when you try to load it, it takes a lot of time. So he offloads it asynchronously, and it allows you to calculate it in the background and create a new time series based on the result of that heavy query. Another example is around alerting rules. which again, it's just a fancy word to take a PromQL, take a threshold. If the result of the PromQL exceed the threshold that you defined, it fires an alert. So Thanos took those two responsibilities and separated them into a different component named Thanos rule. Thanos rule is kind of scalable, more scalable than Prometheus, that's for sure. And now we can have almost unlimited number of recording rules and alerting rules. So let's go through which responsibilities Thanos took from Prometheus, and by that help Prometheus to be more scalable. I don't know if it's obvious or not, but in a Thanos environment, you also have Prometheus. Prometheus is still responsible for two main things. A is the target discovery. That's actually the question, which services, which pods do I need to scrape? Do I need to download their data? The second job that Prometheus still have is to scrape the data, which is actually the question of how to get to download the data from the exporters, from the endpoints, and add it into the Prometheus time series database. We already talked about Thanos rule, but we took something for granted because we assumed that Thanos rule in some magic goes and query the data. So no, Thanos has a lot of querying services which we will mention. And okay, let's go through those. There are a few. First is Thanos query frontend. Thanos query frontend is the top level component in which you don't have to use it, but it's advisable. So it's the top level component in which you run the query in front. The next level will be Thanos query. I will explain a moment about Thanos query frontend, but Thanos query is the actual component that does the evaluation of the query. So the idea is that you send the query to Thanos query frontend, it sends it to the underlying Thanos query, the magic happens and it returns to Thanos query frontend. What Thanos query frontend knows to do is, for example, it knows to cache the result. So if you ask for, 1 hour of data and 1 minute later you want to do the same query again, Thanos query frontend will understand that and only will query for the delta of the data. Another cool thing that Thanos query frontend knows to do is to take, let's say that you decided to query something for 24 hours. So it knows to take the 24 hours time range and break it into smaller time ranges. Why would you like to do something like that? We've mentioned the underlying layer, which is Thanos query. So Thanos query, think about that if you will try to query those 24 hours within a single pod of Thanos query, you will actually, it might get out of memory. That's one option. The other option, it won't get out of memory, but it will work really slow. So the idea is that if Thanos query frontend can take that 24 hours query and split it, by 6, then the underlying layer will receive much smaller queries. It will be easier to process. And I didn't mention it, but you can have more than one Thanos query. It depends on you. And eventually, if you have multiple Thanos queries, it means that your query can run and return to the user faster. Both of them can scale horizontally. Both of them are stateless, both Thanos query frontend and Thanos query. The last service in the querying part is Thanos store. Thanos store is the component that actually goes to the S3 bucket and gets the information back. It goes back to Thanos query frontend. Thanos store knows to run either stateless or stateful. It's recommended to run it stateful. I will explain a bit later why. Okay, so something that will sound a bit odd. Thanos itself does not know to communicate with Prometheus. Simply put, Prometheus does not implement the Thanos store API, so Thanos does not know how to communicate with it. So there are a few solutions. I will talk about one of the solutions, is using Thanos Sidecar. Thanos Sidecar is a small service that you need to put along with the Prometheus setup. It can be either another service, another process inside a physical server. It can be another container within the same pod. And the idea is that both Prometheus and Thanos are looking on the same data set. So eventually, Thanos knows how to query the data, and it's not only that. I mean, Thanos query frontend knows to call Thanos query, that knows to call Thanos store, that knows to query that data. Okay, so the secondary role of Thanos sidecar is actually to do the uploading of the blocks into your S3, I will say compatible storage. I will explain why later. Okay, so we talked a bit about Thanos, Prometheus, and I guess that it's pretty obvious by now. We decided to migrate from the physical infrastructure into Kubernetes. Why? I will state the obvious. Kubernetes is highly scalable. Once you set up the environment, the Thanos environment within Kubernetes is really easier to manage. And it obviously makes the system more resilient. You can recover easily from incidents and so on and so on. So just to summarize, we went from a very simple architecture, like you see above, where each team has a single Prometheus server, well, 2 Prometheus servers, and into something a bit more complex, which is that. But just to say some cool buzzwords, it's a multi-service, highly scalable, fully durable Kubernetes managed service. So, in the new infrastructure, we chose to shard Prometheus even further. I mean, at the beginning, we sharded Prometheus per team. But we understood that if we want to live inside Kubernetes, well, that won't be such a good idea. And why? Because if we have, for example, a physical server that has 128 gigabytes of memory, yes, we can have large pods within Kubernetes, but the scheduler, well, he might not like it so much, or let's put it another way, the scheduler might work better with smaller pods. So we understood that in order to have smaller pods, we need to have, well, less data within the pods. So what we actually decided to do, okay, if we'll have smaller pods, the shards will be smaller, and we could, well, take the same workload into multiple pods. Okay, so what we actually decided to do is to add additional sharding layer, which is by targets, which means that, let's imagine that we have 500 pods, and we are now sharding them. We're telling, okay, we have 500 pods, we have 10, we want to have 10 shards, and then each shard will scrape 50 targets. It means that each shard will hold less data, and that's really more scalable. And that will also, that split allows us to theoretically have unlimited, scraped unlimited amount of metrics. I know that there are some caveats on that, but we can discuss it later. So at this point, if we'll recap the infrastructure, the components that I described earlier, it really makes a perfect fit to add Thanos on top of it. Why? Because we went from an environment which we had one Prometheus server into an environment which, well, you have multiple Prometheus servers for the same team, which means that if I, as a developer, want to find my metric, well, one option is to go through, I don't know, 20 shards, and maybe I will hit the right one and I will find the metric, or just use Thanos query frontend and Thanos query and Thanos store that will give me some upper viewability of the data. Okay, so at this point, we were really very proud in our infrastructure. We were proud in the fact that we no longer need to manage physical hardware. Well, someone else obviously has to, but it's not us. And it was fast, it was reliable, and we could sleep well at night knowing that if a developer now decides to double the amount of metrics that we need to support, we really can do it in a click of a button. But then the GCP bill came. We were not happy anymore. Apparently, Thanos likes to communicate with the S3 bucket, and it likes to do it a lot. And it's not that it likes to do it a lot, it also does it when we are not communicating, when we are not querying it. I mean, it does it in the background the whole time. So let's try to understand which components of Thanos does the communication with the S3 bucket. Okay, so first one is kind of the obvious, Thanos Sidecar. We said that Thanos Sidecar is responsible of uploading the data to the bucket. So in our case, we didn't care about that because in our architecture, it's ingress data, so we really don't care. The other one is Thanos rule. I also mentioned earlier that Thanos rule create recording rules. Creating recording rules actually takes and create a new time series, which means a new metric. And that's obviously need to be uploaded to the S3 bucket as well. So again, upload, we don't care. Okay, Thanos store, that's also a bit obvious. We said that Thanos store is the component which is responsible to do the actual download of the blocks into Thanos. That means, in our case, download, we need to pay. But that wasn't really the big part of of what we paid. Eventually, in our Thanos store, in order to understand which blocks it needs to download, it keeps an index. And not only that it keeps an index, it keeps an index and you need to update it every 1 minute by default, if I'm not mistaken. That means that it scans the entire bucket periodically in 1 minute, and that allows to prepare the index. A lot of API requests, really a lot, and I didn't mention it yet, but like Thanos query, you can have multiple Thanos stores that will allow, well, faster operation eventually. And okay, so I mentioned that Thanos store can work either stateless or stateful. That's also part of that, because if you decide to work stateless in a Kubernetes environment, then your pod might be evacuated for any reason. Let's say that you are in a machine that a pod with higher priority entered the machine, and you are evacuated by the scheduler. So if your pod gets restart and you're stateless, then the entire index needs to be rebuilt. And if you're stateful, well, you only need to take the delta, less calls. Okay, I did not mention compactor yet, and in our okay, so what compactor actually does, what the part that we care about, it's something that is called downsampling. So the idea behind downsampling is if you have okay, when you scrape the data, so right afterwards you do want to see all the raw data, but after a few months, maybe you don't need the raw data itself because you just do some aggregation based on that. And maybe you cannot really see the raw data because you have a lot of points. Then your browser just won't support it. So downsampling is a cool feature which Thanos compactor does, and it takes like 5 points of data and makes it into one. And regardless the value that it gives it, it saves all the aggregational data, the original aggregational data of those 5 points, which is cool, which is very handy in the future. You can also in the future remove the raw data and then maybe save space, but that's not really the point of it because space is cheap relatively, S3 bucket. So in order to do that, Compact needs to obviously download the blocks. It needs to keep an index of what is downloading, like Thanos store, which obviously a lot of API calls, and eventually it needs to upload the data. So whatever way you will look at it, that's a lot of AI operations and a lot of cost. Okay, so let's talk a bit about range queries, and we'll have some cool graph. So range queries is what happens behind the scene when you go to Grafana and ask for the last 30 days of data. So in a Thanos environment, not all the data is necessarily pulled from a single place, which means that we've mentioned it with the physical infrastructure, but also when we live in Kubernetes, each Prometheus pod has some retention on it. And that's actually the fresh data, the data that you would like to see instantly when something happens, the data that you want to be alerted on. So the second part of the data is the data that we've uploaded to the S3 bucket. So obviously, when we want to look at 30 days of data, both of those data sources will be used. So what we understood at this point is that, okay, we have two kinds of storage. One kind of storage is relatively not cheap, let's put it like this. It's the storage that we attach to Prometheus, but the operation does not cost anything. And the second type of storage, it's very cheap, but the operations cost a lot, especially in the scale that we're working at. So we understood that we need to, we took it as some kind of tiers, and we understood that we need to introduce a new tier to our system, where it will be a local storage. We won't be saving a lot of data there because, hey, it's expensive, but we won't be paying for any of the extras that we need to, to scan the bucket. So the next question would be, okay, how much data do we want to save in that local tier? So we went through and we started investigating with Thanos Query Frontend and with talks with the developers, and we understood that usually people use between minus 14 to minus 30 days of time range. So that's exactly what we did. We introduced a new storage layer, and we had also to build two infrastructures, two Thanos Query infrastructure. One when someone uses the local tier, and one when someone uses the remote one. And the idea is that based on the time range that a given user asks for, then we know from where to take the data. So we decided to work with the fancy architecture again. We decided to work with the MinIO as a S3 compatible storage solution. It's an open source tool, really cool one. It implements, you can work with any S3 client against it, so that's cool. And because we live in a physical, our core infrastructure is still physical, we decided to go with Ceph and Rock. I didn't mention, MinIO needs to work on block storage. And because we didn't want to buy some very expensive block storage, we chose Ceph and Rock. Ceph is a great open source project, software-defined storage over commodity hardware, which means that you can take any server and just run a sophisticated storage on top of it. Rock is a kuberneres operator. It's a CNCF project. It makes it really easy to manage Ceph on top of Kubernetes. So now, we don't need to upload the data into the S3 bucket anymore. We need rather only to upload it locally, at least on the first stage, from which later on, using Thanos Replicate, which is again another cool tool, we can replicate the data from one bucket to the remote one. Okay, so doing all that eventually allowed us to reduce 90% of the cost and the majority, obviously, of the API calls that we had against our remote S3 bucket. Another thing that we've made along the way, because I've mentioned that we had two different infrastructures for Thanos Query, Thanos Store, depends on which tier do you query, then we also had a different interval from when we want to refresh the bucket, because when we're looking at the local bucket, where the data is uploaded constantly from all the shards, then it needs to be updated constantly, really every minute, but we don't care, we don't pay for the API request. However, for the remote one, which keeps data, let's say, from minus 30 days up until 1 year, the data there does not change constantly, which means that we can afford ourselves to do an update, let's say, every 30 minutes. And from the user perspective, it will still be okay. So that obviously reduced the cost as well. Another cool stuff that actually happened is because of the way that our infrastructure is built, then Grafana originally sat on the physical data center, and the GCP bucket sat on, GCP. And it means that when the users pull data from GCP, it took time. And when we introduced the local tier, it all began working a lot faster. What about the cost of the local storage? Did you get it for free? No, we did not. But the price was really neglectable in opposed to the price that we paid for GCP for the API actions. Okay, some takeaways. Honestly, I don't have like a straight cut to the chase takeaways, because this is our story, and obviously your infrastructure will look a bit different. But remember that what I told at the beginning, Thanos really likes to communicate with the S3 bucket. Take that into consideration while building your infrastructure. Okay, so last thing, I'm hiring, it's not Outbrain hiring. If you found this interesting, this is a 1 year old project. We're doing a lot more than that since. Then I don't have a cool QR code, I apologize, but feel free to apply, and I'll be happy to have you. Thank you.